There I will have 3% plus 1 plus 1. Because the one that was coming here is going there, it's not able to pass, it's going here, but you have also 1% of this one going there, and 1% going here, so you see that you are, let's say, accumulating the problem with a much larger amplitude, and you will finally have all these percentages that will come back very quickly here, and you could have the full row here, the full row that is separated. I mean the full row, the full circumference. And the problem is of a much larger amplitude. Much larger amplitude. So compared to what I had before, where 0.1%, 0.2% of the total mass flow rate was influenced by the problem, here I can have 10, 20, 30, 40% that is influenced by the problem. And that means that here behind, I will have a decrease of the performance. And I'm here. I'm here. And if I'm here, so you see that you will go into this direction. You will continue going into this direction. Of course, this is a zone that is hard to identify because it's very hard to detect the appearance of the problem, but hop, you will have the full system that will be influenced by the appearance of this phenomenon. And that's why we give to this phenomenon that is of a much larger amplitude. The amplitude here from a pressure and mass flow rate point of view is much larger. We give another name. It's also a stall, because you see it's coming from a separation that we call a stall, but this is originally a leading edge stall instead of a trailing edge stall. But as the consequence is totally different, leading to a real impact at the level of the mass flow rate and at the level of the pressure and temperature and situation that you have here behind, we will not call that a rotating stall anymore. It's not rotating because you are influencing the full problem, and it's not rotating anymore. It's also not called a stall because it's more severe than that. And this is what we call a surge. And what is leading to the fact that maybe the same problem originally is becoming a surge instead of a rotating stall? There can be a lot of reasons. There can be a lot of reasons, but one of the reasons is certainly the dimension of the blade. The dimension of the blade. So, if you have a long blade, I'm explaining it like this, and if you impact the blade at this position, so you see it's a problem of mass flow rate. So mass flow rate, this is not proportional with R, this is proportional with the surface, and this surface here with the same R here and there, this surface is much larger than this one. The surface of this ring is much smaller than the surface here. So you have much more mass flow rate passing here than there. And so if you have a certain height, a certain delta R that is impacted here, and if you go to the last stage, so this is, let's say, stage 1, and you go to the 10th stage, the 10th stage is much smaller blade because the compressor is built like this with a compressor blade that is here, and the compressor blade is becoming smaller and smaller, and if you continue, you have a very short blade at the tip. If you impact the blade over the same delta R, so same stone, impacting the same delta R here or same delta R there, same delta R here, you see that the situation at the level of the mass flow rate is totally different. Here it's a very small mass flow rate that is impacted. Here this is a much larger mass flow rate. And here, because the blade is much smaller, proportionally, this is even a much higher mass flow rate that is influenced. And so you see that the ratio, so the value of H, if we call that here H, is a lot, the value of H is a lot influencing the problem. And so if you decrease H, you are going into much larger problems in the compressor in general. So you see that it's, let's say, closely related if we are in, let's say, the first stages or if we are in the last stages. And we could say, globally speaking, that in the last stages, you will not have rotating stall. In the last stages, you will have most probably surge. Whereas in the first stages, you could have rotating stall and you could have surge. Be careful, I'm speaking about the first stages and the last stages. I'm not speaking about the rotational speed, because the rotational speed there and the rotational speed here is the same. I'm speaking about the stages, okay? And what will have also an effect on the situation, this is the airfoil shape. So depending on the shape that you have here, depending on the type of airfoil, so what I have represented here is not exactly correct. Depending on the shape, you will have an airfoil that will have such a curve, because it is an airfoil that will have a trailing edge separation, or you will have another airfoil that will have this shape of CL in function of the angle of attack, because this airfoil is flatter and will detach, will separate directly over the full length or the full chord of the blade. Okay? Of course, you could say, this is a bit an image, because it's not always like this in reality, because this is not the same blade that is doing trailing edge and leading edge separation, but most probably you could represent the problem as joining, because when you are separating, so this point here is there, this point here is there, this point here is there, and this point here is there. So you see that a trailing edge separation, when growing, is becoming a leading edge separation. And so if you would have a large trailing edge separation, it's also leading to surge. So you see that rotating stall can degenerate in surge. Why? We don't understand exactly. And that will be something that we need to analyze. What makes that we are going to this situation or to this situation? I have explained one feature, which is the amount of mass flow rate influenced by this velocity triangle problem, or angle of attack problem, or CL problem. But there are certainly other features, other, let's say, phenomena that makes that you are sometimes being stable in this case, or degenerating in this situation. Okay? Very often people are saying that it's related not with H, but with H divided by the chord. We need to be a bit careful with that. Because it's depending on other features and not only on H divided by C. It depends on the situation. So you see, when H is decreasing, you have H divided by C that is decreasing as well. When C is increasing, you have also that H divided by C is decreasing. But when C is decreasing, when you have a blade like this, so you are less sensitive to the trailing edge separation, because the trailing edge needs to separate more and more and more depending on the length of this chord. So speaking in H divided by C must be taken with care. It depends on the type of profile that you are discussing. But you see that these two phenomena, rotating stall and surge, they are quite similar. One, rotating stall related to small part of the blade, small m dot, not leading to very high consequences, almost no consequence, I would say, at the level of the performance of the compressor, but mechanically it can be dangerous. Whereas the surge is quite impacting the mass flow rate and the performance of the compressor and the pressure ratio, but it's not so dangerous from a mechanical point of view because it will be a phenomenon that is at a much lower frequency. So, because you see, you are entering into the blade row and then you are leaving the blade row. When you are leaving the blade row, what's happening? The situation is becoming again, let's say, normal. So you are re-establishing the situation. So maybe you will enter again, but the situation had a problem at the beginning, so it will leave again and come back again and leave again. Maybe you could have a problem like this, or maybe it will be only going out, going back, and re-establishing the flow. It's hard to know exactly what will happen. But it will be a phenomenon of a much lower frequency, because you need to go through the row and exiting. Through the row and exiting is much less frequency than related with the rotational speed of the system. So it's a higher amplitude phenomenon from a fluid point of view, but a much lower frequency phenomenon from a mechanical point of view, and so the problem is, let's say, quite different. And you may work with a system if you are with a low delta sigma, you may work with this situation existing, you may not work with surge, that is very dangerous for the situation. What is dangerous with surge? It's mainly the combustion chamber that you have here behind. Because you see, surge is influencing the amount of m dot. Here, m dot is almost not changing. 0.1%, 0.2% is not a lot. Here, you are changing by a few percents, maybe 10%, 20%. But you are still injecting the same amount of fuel here. That means what can happen? You can increase a lot the TIT. And you can burn the turbine blades that are behind. The second thing that could happen is that you have an instability in the flow. So you see that 100% is entering, and then you are separating on all blades, so maybe 50% is only entering, and then 50% is going away, and then you are reattaching the flow, 100% is going inside, detaching